Now I'm going to talk about pH. So if we want to describe the acidity or basicity of a solution, it really is based around the concentrations of hydronium and hydroxide. They are linked together by by our equilibrium, and so either of those will describe the solution. But the thing is, those concentrations are generally really low. They also vary over orders of magnitude. So they're not really that useful kind of in a practical sense. So instead we use pH. And so pH is just, we take the negative of the base 10 logarithm of the concentration of hydronium. And the P in pH literally stands for power. So what we're trying to take here is kind of just the power, or like the exponent from the scientific notation description of the hydronium concentration. And so the idea here is that this will give us a more clean description, an easier to talk about description of the hydronium concentration that also doesn't vary, isn't over quite orders of magnitude, because you're describing the order of magnitude. When you're using, a logarithm, it's the same thing as asking, a base 10 logarithm, 10 raised to what power gives me this number? And so, 0.0001 is 10 to the negative 6. So the log of that number is negative 6. And you'll notice that the logarithm of numbers smaller than 1 are always negative. And so because our concentrations are generally going to be below 1, that's why we are putting the negative sign when we take the negative logarithm to give us a positive sign in our pH. So common mistake is forgetting that negative sign. pH values that we're going to be working with are always going to be positive values. So the purpose of pH is to characterize the acidity. We know that hydronium concentration that we've used previously also describes acidity. So how do we translate that? So pure water, a neutral system, concentration of hydronium is 1 times 10 to the negative 7. If we take the negative log of that, we just get 7. So a neutral aqueous solution has a pH of 7. In the NaOH example that we saw previously, the hydronium concentration was 1 times 10 to the negative 13. So if we take the pH of that, we get 13. Okay, so pHs greater than 7 correspond to basic. So it comes from, again, we're kind of inverting. We know that when we're dealing with concentrations, a power that is more negative than negative 10 to the negative 7th is a basic solution. In this case, that more negative becomes, in the case of pH, more positive. So pHs that are greater than 7 correspond to basic solutions, and pHs that are less than 7 correspond to acidic solutions. So we can kind of we have another way to describe solution acidity. We want to remember those sort of relative descriptions, less than 7, greater than 7, those sorts of ideas. So the pH of rainwater is 6.2. What is the concentration of hydronium ions in rainwater?
So the pH of rainwater is 6.2. What is the concentration of hydronium ions in rainwater? So concentration of hydronium ions, again, that's going to be our H3O plus. And this is something we very frequently want to know about a solution, especially aqueous solutions like rainwater, where we want to know what's going on, what's the acidity, what's the kind of molecular level description of this solution. And so when we're dealing with hydronium, there's going to be a lot of relationships. We have a lot of equations that describe and relate these different aspects of these different properties, hydronium, hydroxide. Now we have pH. So we have pH, and the pH has an equation associated with it. So whenever we have any information about pH, we're given a pH value, we want to know a pH value, we want to recognize that there is an equation for pH that we can use. That's going to be kind of our standard, that pH is equal to the negative log, that is a base 10 log, of the concentration of hydronium. So if I want this, I can directly relate that to the given pH, the 6.2. And so hydronium concentration and pH represent the exact same thing. Hydronium concentration is like the actual chemical information that we want, but pH generally is just an easier number to talk about and describe. And so they can really kind of go back and forth. But they mean contain the exact same information. How many hydronium, what's the hydronium concentration, right? And so what we do, we plug in 6.2 is equal to the negative log of the concentration of hydroniums. And so we want to isolate this so we can get the negative 6.2 log of the concentration of hydronium. And so if I want to get rid of the log, a logarithm is asking 10 to what power gives me this value. So in order to undo a logarithm, you can just take 10 to that power. So we would get that 10 to the negative 6.2 is equal to the concentration of hydronium. Because really this is like you have 10 to the log of the concentration of hydronium. So log is asking 10 to what power gives me hydronium. So you're basically taking 10 to that power, which gives you the concentration of hydronium, just straight up. And this, you use 10 because it's a base 10 log. So concentration of hydronium is 10 to the negative 6.2. We can use calculator. An anti-log key would also accomplish this. You may also have a 10 to the, like a little 10 to the key on your calculator, which accomplishes this. You can plug this in explicitly as an exponent. And we get that the concentration of hydronium is equal to 6.3 times 10 to the negative 7 molar. And so we've got our number, we've got our concentration. This is what's actually going on at the molecular level. And one of the things we want to do whenever we get something like this is when we're dealing with acidity, acids, bases, we can always kind of check, are our numbers consistent? So our initial pH was 6.2. That is below 7. So this would imply that we are dealing with an acidic solution. So we think that this thing has more hydroniums than hydroxides. This solution has been pushed, the balance has been pushed towards the hydroniums. So if we look here, is this a consistent value to indicate an acidic solution? And the answer to that would be yes, because we can see that this thing is greater than 1.0 times 10 to the negative 7 molar. Not a lot, but 1.0 times 10 to the negative 7 molar. This corresponds to neutral. So because the hydronium concentration is greater than 1 times 10 to the negative 7, that is consistent with this being an acidic solution. It's not very acidic, consistent with the fact that the pH isn't that far below 7. So it is barely acidic. Rainwater is barely acidic according to pH, barely acidic according to hydronium concentrations. And so we can see this pH contains the exact same value. It's just an easier number to look at, easier number to talk about, easier number to diagnose. Is it acidic? Is it basic? And that's why we use it. But this relationship, pH is equal to negative log of hydronium, can use a lot. We can also use the fact that the concentration of hydronium is always equal to 10 to the negative pH. So that is a generically true equation that we can always use to go from pH back to hydronium concentration, if that's what we want.
So when we're talking about the pH scale, we can use it to characterize acidity, and really what we're characterizing is the concentration of hydroniums underneath. And each one pH unit corresponds to a 10 times change in acidity. So going from 9 to 8, 10 times more acidic, 8 to 7, 10 times more acidic, 7 to 6, 10 times more acidic, and this just continues on. Every time you're getting 10 times more acidic. So each pH unit is the same proportional change. One of the things to note about that is when you have pHs that are really close to 7, say really close to being neutral, the absolute change is really, really small, right? At pH 7, it's 10 to the negative 7th molar. At pH 5, it's 10 to the negative 5th. That is barely a change in the absolute value. It may be 100 times more acidic, going from 7 to 5, but the actual amount of hydronium that's present isn't that big. Because you're dealing with you're starting small and multiplying it by 10, it's still small. So it is important to kind of recognize that, something that is pH 5 really isn't that crazy acidic. It is 100 times more acidic than neutral, than pure water. Pure water just really isn't. And actually, most of the water you get out of the tap is probably like pH 4 because of how much air is in there. CO2 in the air turns into acid in the water, and it can lead to acidic water. But it's just not that different from pure water. You're not really noticing it. Now, once you start to go from, say, pH 1 or pH 0, those are some pretty serious changes where you're looking at you have a large concentration that's changing by a factor of 10. That's where you really do start to see really big changes in the absolute acidity. And so one of the things about this is you'll see things like pH 9.5, and you'll see like alkaline waters like this one. And so the pH is 9.5. That's not pure water. But the thing is, it's not that different from pure water because, again, it's pH 9.5. It is over 100 times more basic than pure water, but there's barely any hydroxides in pure water. There's not a lot of hydroxides in this. So the reason why that pH difference matters or noticeable is not because it's 9.5, but because of what drives the pH difference. There's carbonate in most of these is what drives the change in pH that you see, or why they become basic. That's not a very good, carbonate's not very good at causing pH to change, so you have to use a lot of it. So you get a large change in the taste because you're tasting the carbonate, which is a base. So you're tasting that, and that can potentially cause effects inside your body. But it's not necessarily that it's not this huge change in the pH of the water that's really causing much of a change. Plus, it's important to note your stomach is acidic. It neutralizes all of that stuff once you consume it. So pH measures acidity of aqueous solutions. So when you have an aqueous solution, the pH is a metric for how acidic that is. It's important to note it's not an inherent property of any sort of substance. Pure water has a pH of 7, but outside of that, it's not necessarily that hydrochloric acid always has a certain pH. It depends on what the concentration of the acid is and how that acid affects the equilibrium of the aqueous solution. So there's a lot going on in there. There's a lot of linkages in there that we want to be mindful of how those sort of affect or contribute to different pHs. And don't worry, we'll spend plenty of time figuring that out. There's another very similar metric called POH. You'll note that O is slightly different. The P still stands for power, so there's still the P, there's still the negative log, but now it is OH, so you use the concentration of hydroxides. Again, hydroxides are part of the equilibrium with hydroniums, so you can have the same idea. You're just looking at the hydroxides. Instead of asking how acidic is the solution, you're asking how basic is the solution. So pure water, the POH is 7, just like it is for pH. But now if you're looking at, say, hydroxide, our hydroxide example, whereas the concentration was 0.1, you got a POH of 1. So the difference between pH and POH is just swapped. Low POH values correspond to basic solutions. High POH values, ones that are greater than 7, correspond to acidic solutions. So high POH means not basic, which is how you can get the more acidic solution. So it's just an opposite. It's opposite of pH because the hydroniums and the hydroxides, they're kind of the two sides of this coin, acidic versus basic. If you take the KW expression, you can do some algebra, you can use some logarithm rules, and you can actually come up with a relationship that 14 is equal to pH plus POH. So this would be true for any solution, that the pH plus the POH of that solution, those two values have to combine to be 14. So you can use that. You can see that from the fact that like things that are acidic have really low pHs and really high POHs. And again, it's that sort of kind of seesaw, that sort of balance between as the hydroniums go up, the hydroxides have to go down, and vice versa, right? Those concentrations have to go up and down. They have to balance each other. Same thing that if the pH goes up, the POH has to go down. They're linked by adding up to 14. They always add up to 14. And so that's a relationship you can use if you want to go back and forth between these representations, pH and POH, for a single solution. The pure water, they're both 7. They add up to 14. NaOH, that NaOH example we did, pH was 13, POH was 1. They add up to 14. They will always add up to 14. And so if you know one, you inherently know the other, because 14 minus pH gives you the POH. So there's a lot of ways that we can describe whether or not a solution is acidic, basic, or neutral. We can look at the relative amounts of hydronium and hydroxide. We can look at the absolute concentrations. How do they compare to the 1 times 10 to the negative 7 of neutral solutions? What's the pH? What's the POH? All of these relationships are all describing the exact same equilibrium description. The concentration of hydroniums and hydroxides is always linked by the equilibrium description of the autoionization of water. That's always the chemistry that's going on. That's always linked together. And we know that those are always balanced. So what does that look like for our particular solution? Okay, one more video in this set. Maybe a participation question in that video. Who knows? We gotta watch and find out. I'll see you there.